So, we are going to discuss about the EBSD today. So, I will discuss first the EBSD principles, and then I will tell you how the integration of the EBSD with computer has changed the analysis of the EBSD patterns and then also the related aspects during the study of the deformation behavior and the texture study of materials. And finally, I will show you how the EBSD actually is done in the real microscope. EBSD has a long history as we look into the papers about 90 years back. In 1928, Kikuchi from Japan first time observed Kikuchi patterns or Kikuchi lines, and although it has been reported that he did not observe, he postulated that there will be a possibility of formation of Kikuchi lines in the electron diffraction patterns. And in fact, Kikuchi went on later on when TM was discovered, and it was observed these lines do exist, and they are basically due to the inelastic scattering of electrons. Then after about another 26 years, in 1954, black reflected Kikuchi lines were observed in TM by Alam. Then in 1969 to 1979 saw a huge change in the SEM techniques of EBSD. Three different types of diffraction patterns were detected. One is the SACP, that is selected area channeling pattern, the one which I have discussed in the last class, where in fact 10 amps micrometer resolution was obtained by Joy et al. At Oxford University. And at Bristol University, Digney et al. Or Digney and others actually have found out the coastal diffraction patterns with a practical image resolution of 20 micron. Finally, EBSD came with 1 micron practical resolution by Venables et al. At Sussex University, again from England. 1980 to 1984 saw the extensive uses of computer in indexing EBSD patterns, and then from 1990 onwards we have fully automated EBSD systems with half transformation possible. Again, major contribution came from University of Yale, University of Towson and Rees. And from 2000 onwards, that is in the 21st century, we have very fast automatic pattern analysis systems. Obviously, I have not listed the improvement in camera resolution and camera activities in this EBSD. So, now it is possible to have high resolution EBSD. In fact, people are doing in situ EBSD experiments, which we will discuss, and it is even possible to have high current EBSD. So, I will not be able to discuss all of them, I will discuss some of these during this lecture. Let us first look at the basic theory of EBSD. As we know, the electrons from a source like tungsten filament or lab-6 filament or FEG in SEM, they accelerated at a very high voltage 20, 30, 40, maybe 60 kilovolts, depends on the microscope, and allowed to fall on the sample surface. So, therefore, because of this interaction with the sample, the electrons will undergo scattering. One of the effect of this interaction is scattering, and the scattering actually can create a point source of electron with all possible trajectories within the material. Let me show you example. Suppose this is a material and we have an electron, and once the electron falls on the sample, you can see it is going to create a point source here, and from where the electrons actually can move in different directions. In the crystalline materials, you have the atomic planes, and these crystal planes can actually cause diffraction provided Bragg's law is satisfied. So, therefore, in crystalline material, if you have number of crystal planes sitting on in the material and the electron falls, and they can also actually get scattered, but in some cases if the crystal planes are actually oriented properly with respect to the electron beam, so that Bragg's law can be satisfied, we can have diffractions. And as I said in the last class, if we change the beam orientation, we can have the channeling of backscatter electrons, at the same time the scattering of backscatter electrons inside the crystals, and this can give rise to black and white lines, and these are actually basically Kikuchi lines. So, this is basically the reason for origin of the EBST, the scattering or rather Back's law dominated or determined scattering of the electrons in the material. So, therefore, as you know, all of you know, because you have done the preliminary course on the characterization, the Bragg's law. EBSD occurs due to basically Bragg's diffraction, and we know Bragg's law is given by 2D sin theta equal to n lambda. Everyone in this course will have idea about this particular equation, which Henry Bragg and William Bragg they discovered long back. And as you know that if the electron beams with a certain wavelength falls, wavelength lambda falls on a atomic plane of spacing d, it can get scattered by the Bragg's law with an angle theta, satisfying 2D sin theta equal to n lambda, where n is basically order of reflection. Normally it is 1 in case of X-ray, but in case of electron diffraction it can be more than 1. So, therefore, whenever the electron beams are getting scattered by the lattice planes, if they satisfy the Bragg's law, then there will be diffraction, and then we will be able to detect the diffraction by using camera. We will have the EBSD patterns, that is the basically things. So, if we want to go even detail of that scattering from a single lattice plane, so if we look at it, that we know that each lattice plane can be indexed by HKL by Miller-Babelis index or Miller indices, gives rise to 2 diffraction cones. Let us see that how it is operates. So, suppose you have a crystal like this, which basically cubic is shown like that, and suppose this is the 110 plane in the cube, and then if we have electron beam falling on this plane, and then they are getting diffracted. So, this diffracted beam will create a cone of intense electrons. These are all can be easily borrowed from the X-ray diffraction. Anyone who have studied X-ray diffraction, we know that even in X-ray diffraction camera also we have cones of reflections coming out because of the diffraction from a single crystals. And then if we have a phosphor screen, we can detect these lines, with these lines actually called Kikuchi lines. So, this is basically from a single lattice planes. Now, you have a multiple crystal present in a crystal in a sample. So, therefore, there will be different kinds of patterns or different orientation of the Kikuchi bands will come different from the different planes of the crystals, and then we can get actually a complex EBSD pattern. So, for ACM electron wavelengths basically they are much larger than the TM, the opening cone angles are found to be close to 180 degrees. This cone angle which is coming many times has been found to be 180 degrees, very large, because wavelength is even larger here. So, 2D sin theta equal to n lambda. If lambda is large, then theta will be large, because sin theta is proportional to lambda. Now, obviously, one can look at the scattering from the 3D lattice planes, and suppose we have just basically 20 kilovolts electron beam striking the sample, which is tilted to 65 to 75 degrees with respect to the beam, and then we can think of like this. Suppose this is a silicon unit cell, again we have a basically diamond cubic structure, electron beam falling on this, it can get scattered, different planes will scatter and form these Kikuchi lines, which is shown in this picture here. And then on the phosphor screen, the crystal structure at the point of incidence of diffract, the electron beam according to Bragg's law, and each lattice planes basically you can look at it, each lattice plane 110 or 100 type, they are giving rise to 2 sets of basically cones. One set is this, other set is this. So, whenever these 2 sets hits the phosphor screen, they leads to 2 lines, and these 2 lines actually called the Kikuchi lines. So, we are basically terming this as a Kikuchi lines. Basically, we are naming them by the scientist called Kikuchi. So, in actual sense, this is taken from J. Hedgeling. Actual sense, we can actually see these Kikuchi lines during the experimentations if we have a camera put inside the ACM. So, if you see this is a sample which is tilted with respect to the beam at about, or respect to the normal plane at about 65 to 75 degrees Celsius, and then the electron beam is falling like this. This is basically schematic. Obviously, one cannot image the electron beam by using normal camera, electron beam is invisible. So, and then it generates this cone actually has 2 two cones actually. So, they fall on this phosphor screen and screen produces two lines on the screen. So, this is the origin of the Kikuchi patterns or diffraction patterns. And in a two dimensional plane, as I have shown here, this is a crystal, this basically creates these lines and bands, and these bands has, you will see the axis or meeting points. These meeting points are called zone axis in the literature, because they are like different roads coming from different places and meeting at certain points. We know that there are junctions. So, these are actually called zone axis. There is one here, there are 4, there are many more, one there actually. So, one can actually index the zone axis using proper indexing scheme, again using Bragg's law. Well, that is very what is called general one, so that we can get a very nice diffraction pattern, but at the same time one must understand that all the backscatter electrons which are falling on the sample, they may not produce the scattering which will be detected by the skin. So, therefore, there will be as only a small proportion of the electrons arriving at the phosphor schemes are diffracted. So, bulk of these electron beams are not diffracted, they will undergo multiple diffraction and then getting absorbed inside the material, or maybe coming out, but then they will not contribute to this Kikuchi bands. So, therefore, a pattern is always superimposed with on a background. It is just like X-ray diffraction pattern. In X-ray diffraction pattern, you have a background intensity coming from Bremsstrahlung and the peaks which are coming from the scattering due to bags. Okay, so, therefore, this background needs to be subtracted, otherwise we do not get a very nice pattern. These are all actually done in a computer nowadays. So, one can look at in fact, the backgrounds diffraction can be subtraction can be done same way like any radiations, and this is done here. You can see that backgrounds are like this with respect to this is very small intensity, although, but still it has to be subtracted then to get obtain a very nice EBSD pattern. Not only that, as I said in the beginning of the lecture, with the advent of computer only, fast computers, this technique has taken a big lead in the material science research activities. So, images which are obtained or patterns which are obtained from the EBSD camera, they need to be processed, and as you see, the unprocessed EBSD pattern is in fact does not contain much information. So, normally we take several EBSD patterns on a particular case. So, if we select a point on the material and take several EBSD patterns from that, and then we just integrate them. Once you integrate them, signal to noise ratio improves, and then we correct the background intensity, so that the band contrast increases, and in many cases images are compressed, so get even better clarity of the bands. So, these are all routinely done in the computer. One need not bother about it while doing the experimentations, but you must know that these are required to obtain a good quality EBSD pattern. Now, as I said, zones or zone axis just several 2 or 3 slides before. So, zone is nothing but a phase or planes in a crystal with parallel intersections. That is what is shown here. You can see that there are phases which are actually having parallel intersections, and zone axis is the common direction of the intersection obviously. So, if I have several planes, there will be one direction which will be contained in all the planes, that is actually called zone axis. So, in wherever the EBSD patterns or EBSD bands or Kikuchi bands rather will meet in the EBSD pattern, they actually can be defined as a zone axis and can be indexed using a proper scheme. Just to show you that, as I said, these are actually zone axes which are actually taken from germanium syn crystal at 20 kilovolt acceleration, and you can see that these are the actual zone axis marked here by red, and they can be indexed, which I am going to discuss after some time. So, these zone axes are actually carry information about the orientation of the crystals in the geometrical plane or in the material. So, orientation of the grains. Well, that is actually done using half transformations. Half transformation provides a suitable technique actually for deriving the parameters of a straight line, and that is actually bands positions in the EBSD patterns. Let us see how it is done. Basically, EBSD pattern is nothing but XY plot. As we look at it, there is 2-dimensional XY plot. So, what we do is that we convert this XY into rho theta plot. Okay, so, if suppose we have 3 zone axis 1, 2, 3 or 3 bands rather, on the EBSD pattern, then the x is given by this one, the horizontal variable, and vertical one is basically y axis, and then you can see that rho is connected to x and y, and theta which is given by at the top of the this picture, x cos theta plus y sin theta equal to rho. So, we can convert this information from xy space to the huge half space, that is rho theta space, and we can get these bands, because they are called huge bands, half bands actually. So, lines in the patterns can be converted into spots in the half surface, and this is again done routinely by a computer. We do not need to do anything in the real material analysis problem. We go to the EBSD setup. So, the computational power is so much that these are done routinely in fact, or online processing is possible also. So, basically real information which is gathered can be at the same time processed in the same computer by transforming this information from this xy space to half space. And then once you do this, you have to detect the bands, okay, and these bands are detected by using indexing scheme, or that is what is called EBSD pattern recognitions. So, EBSD patterns can be recognized or indexed using several schemes. So, as you know, EBSD pattern obviously are unique to your specific crystal orientations. Even if you know the crystal structure of the material a priori, it is basically depends on how the crystal is oriented in the space, or the grain is oriented in the space. So, this is a very unique thing about this. So, depending on orientation, just like in a TEM diffraction pattern, the diffraction events actually depends on the orientation of the crystal in the plane or in the space. Same thing actually is true for here, but resolution is poorer here. At the same time, you can actually have much largest what's called area can be analyzed in ACM as compared to TM, because thin area is very small in a TM sample, but in ACM you have a large area which can be analyzed. Pattern is controlled by the crystal structure obviously. Crystal structure means space group symmetry, lattice parameter, and precise compositions. If it is an alloy, one is to know the precise composition. Within each pattern, the specific bands or this pair of cones of diffraction represent the spacing of the specific lattice planes, as we have already told you when we are discussing the Bragg's law. Then EBSD pattern recognition compares these patterns of the bands with atlas, which are prepared for the so many years of experimentations to index the crystal orientation required. So, therefore, this is again just like X-ray diffraction pattern analysis. We have the X-ray diffraction taken from a sample, and then we compare with the atlas which is available in the literature. If there is a new crystal, then we cannot index. So, we have to go by again by the standard process of first knowing the crystal structure of the material, lattice parameter, and other things to index it, and then this information will go to the atlas, just like the ICDD database in X-ray diffraction. This also a database. So, that can be used to what is called index EBSD pattern. These are all databases are all given to each and every software which are used in EBSD analysis. So, along with the software database are available. This is just like a WAS manual. It is fully automated now, as I just now discussed, and can be used to index. So, EBSD patterns, let us see that this is taken from pyrites. Pyrites is nothing but FeS2. One can take metal also, but I am showing you. As you see, there is a zone axis here, there, in fact there one, so many, there is zone axis there, there is zone axis there, many. Okay, so basically this is the major zone axis where the many lines are, or many bands are meeting. Now, unique for the crystal orientation obviously and the composition for the pyrites can be more than 100%, 100 degrees for total crystal projections. That is, you can basically obtain for a large angle of diffraction, and physical resolution is nowadays can be obtained of less than 1 micron possible, and some pattern details can also be obtained. Let us show you that a diffraction pattern from specific planes. So, suppose this one is basically a band. So, width of the band is basically 1 by d spacing of the crystal, or the particular plane of the crystal. This is the first order diffraction pattern, okay, as you see here these lines, and this is basically second order diffraction. The blue lines which are shown on the screen, they are actually second order diffractions, and the yellow ones actually first order diffractions. Just like in a TM diffraction pattern, you have first order, second order, third order, or first order and higher order diffraction patterns. So, and this is a major pole axis, as I just told, because there are so many lines are meeting and the points, the bands are meeting at this point, and this is what is called Hodge, high order Laue zones, rings. They are basically same like in seabed or convergent beam electron diffraction patterns. In the convergent beam electron diffraction pattern, you can get 0 order Laue zone, then first order, second order, or 0 order and higher order Laue zones. So, this is a 0 order and this is a first order. So, that is basically a way to read the EBSD pattern. Now, to give you some other example, suppose this is the original pattern of some crystal, and now it can be either manually indexed or auto index. So, auto indexing is done like this, the way I shown you. First the bands are marked by different lines and then they are indexed. This is again computer, done by computer. As you see, this is hexagonal crystal, okay, this is in fact bismuth. So, the different lines can be easily marked. So, in every cases you see one inside there are 2 lines, outside there are 2 lines. This is the first order and this is the second order diffraction lines or QC bands, and this is a major zone axis here, this is another major zone axis, and there are some minor zone axis also possible. This is another minor zone axis here. So, this can be easily compared. So, origin pattern will be matching with this, then we are sure that we have done the indexing properly. So, to index we require many things, not only the crystallographic informations. You need the SEM geometry, that is beam energy, specimen, detector position, and also orientation of the detector, how the detector is oriented with respect to the crystal. Usually which is these are all fixed by SEM, beam energy sometime can be changed, but specimen is also fixed by the user, and detector position and detector orientation are fixed. So, only thing which you change, which you can change actually, beam energy, and this will change the wavelength of the diffraction beam. Crystallography, as I said just now, crystallography is very important because you need to know the sample, crystallographically sample, that is the lattice parameter, space group, all these things are required to be known, and they are actually input for any kind of crystal, and diffraction characteristics to be also known, that is relative diffraction intensities must be known. These are all obtained, all given in the SCPDS or ICD databases of the any crystals. So, but I will show you some example how it is to be done, and it can be calculated as I said. So, let us see how we can create that. We can create this data. So, first let us suppose you have a crystal like aluminum, which is a common metal. You know it has a FCC crystal structure, and with the lattice parameters like ABCs 0.405 nanometers and alpha beta gamma. This is gamma. Gamma is basically 90 degrees, and the symmetry also can be obtained is a cubic. The Laue group is M3M, space group is 225 or F3 bar M, phase center M3 bar M, and unit cell symmetry indices. There are 4 atomic positions, we know that. So, let us see the atomic positions there. Aluminum sits at 000, that is occupancy 1, and aluminum again sits at the phase center 0.5, 0.51, also 0.5, 0.50, sorry, that is occupancy 1, and you can have 0.50, 0.5 occupancy 1 and 0.5, 0.50 occupancy 1. So, you know everything about the crystal by knowing all these stuffs, the lattice parameter, symmetry, and the atomic positions. That is all we need to calculate X-ray diffraction pattern also. So, how to do? To index the EBSD pattern, we must know the relative intensities, as I said, that is of the bands or QQ bands or reflections in the patterns. Just like X-ray diffraction pattern, we need to know the relative intensities of the diffraction peaks, same thing done here. So, and most approachable use is the kinematic diffraction theory, which is very complex, let me tell you. In fact, in TM probably it has been discussed to you, but many cases it may not be discussed to you. In that case, there is no choice other than going back to the books and learn it. Kinematic diffraction theory is what is called routinely discussed in the TM books, and this model actually calculates the structure factor for each of these H scale planes. How it is done? we know the intensity is basically square of the structure factor related to structure factor. Okay, it is basically square of that, and FH scale is given by sigma g equal to g goes to 1 to n Fg is basically atomic scattering factor and exponential minus twice pi I h dot xg k plus k dot yg plus I dot jd, where h scale is the plane indices and x y z are the lattice the atomic positions. This is the n is the number of atoms as you know, and Fg is basically scattering factor for each atom, which can be obtained from the any database. And lattice planes and atomic positions I already told you. So, how do I create it for aluminum? So, let us do that. We know that for there are 111, there are 4 111 planes. So, this spacing is 2.338 with intensity coming to be 100%, because 111 is the most dense atomically dense plane. So, therefore, it will have the largest intensity coming diffraction intensity coming from this plane, followed by 200. Again it has there are 3 such planes with a 69.4% intensity and so on. One can actually go on calculating this for many large number of planes, and EVSD we need to do that. These are routinely done. Obviously, for aluminum is very easy. For other things, other crystals, complex crystal is not easy. One needs to use computers to do that. So, manually doing is very difficult, but aluminum manually this can be all calculated. Well, that is actually way these crystal databases are created, and then these are used to index the EBSD the bands in the EBSD patterns, and then obtain index those patterns to obtain the crystallographic orientations. So, once we know the orientation of the each crystal, what do I do with it? That is what is the basically important aspects one needs to know. Well, as you know, suppose in a crystal there are many grains. I can draw these grains here like this in a material. Okay. So, if you have so many grains, and we know that definition from the grain tells us that each of these has separate orientations. So, what you need to know is from EBSD is that once you put the electron beams on this crystal or on this grain, we can obtain the orientation of this crystal or the grain very easily by doing all these kinds of indexing these patterns from this grain. Similarly, I go to the next crystal or next grain and do the same analysis, and then this and then this and then this, so on. And once we do all this analysis, we can store this information how the crystals are oriented with respect to the physical space x, y, z, and then once you know that, we can basically do this orientation contrast imaging. So, we can plot this data on a micrograph to obtain the orientation information of the grains, each grain. So, that is actually called orientation contrast imaging. So, that means the contrast of this image will vary depending on the orientation of the each grain of the crystal. So, in a polycrystalline sample, where suppose this is to talk about the emission signal how it is dependent on the crystal orientation. In a polycrystalline sample, you have different grains. One is this is another one, this, and the planes are oriented differently on each of these grains. And now, if we have electrons falling on this suppose this particular grain, and then we can obtain the orientations just by doing this. So, we can basically give a grayscale image contrast on this, okay, based on whatever way we define the grayscale, and then we can obtain from this, we can make it darker depending on the orientation of this crystal, and this is again can be done this way. So, that is how one can actually obtain this grayscale level. It depends on the penetration and the emission also. Emission means how much backscatter diffraction is coming out from this crystal and detected by the camera. So, that is how actually this is very simple. This is the simplest possible way of representing this orientation images on the crystal on the EBSD patterns or EBSD from a large sample is done. I am showing you. Let me show you some image. Electron beam is basically scanned in any scanning electron microscope, and sample is tilted. So, rather than positioning the beam on a point on a EBSD, because we are scanning the beam, so we put the different position the beam on the different position of the sample, and there will be sporoscattered electrons with intensity determinant penetrations and crystal orientation obviously, and they are emitted towards the EBSD detector, and these signals are detected by silicon devices or the camera, which is basically Peltier cooled camera and attached to the EBSD detector. and this is how it is done. So, once you have all this information, we can plot it. You can see this is a very large area, this is only 100 micron. So, that means this is approximately 10 times of that. So, 1000 micron is this length, and this is approximately about 600 micron, a very large area scanned, and we can see different grayscale contrast on the image. So, each of these actually showing the orientation of the quartzite grains on the sample. So, this is, you can see that this grain is darker. So, that means this is oriented very preferably with respect to the, so and this grain is brighter, and there are lots of dots, they actually, that means they are actually not contributing to any information to the EBSD pattern. So, that means the first scatter electrons orientation contrast image of variation in crystal orientations, the contrast variation is only here qualitatively. So, you can do that. So, let me just tell you that how this is done in automated or computerized system. Computer control movement of the electron beam across a sample can be done, EBSD pattern can be captured from each point, and that is what is shown. So, you can basically go to each point and capture the EBSD pattern, and this is the pattern from one, index this pattern by using a pattern recognizing software, and then software has either crystal orientations in 3 Euler angles phi 1, phi 2, phi 3, and the phase information per pattern to a database for analysis. So, I am not going to discuss about how these Euler angles are determined, this is again not possible in the short span of time, but one needs to know also. The important to run this manual visual check for solution before even we do this analysis, because computer is basically black box, whatever goes in it comes out. So, if you put garbage in, garbage will come out. So, one must actually run, one must actually see visually these patterns and be sure about it, what you are saying is what you are obtaining, and then do this indexing in a computer. This is again taken from 1 hour sample, this is the grain orientation image, okay, and you can see this is 001 pole figure, okay, and you can see there is a predominant texture, that is why these things are looking black. Those of you who have little bit knowledge about texturing, you can understand, and these grains can be shown to be oriented along different zone axis. Actually, this red is actually close to 001, and blue is actually close to 111, and the magenta is close to 011. So, therefore, one can actually see this different grain orientation and obtain this inverse pole figure, and then find out the where this majority orientation is coming into picture. As you can see, largest cluster is coming here, which is at a angle almost like 90 degrees from the pole, and some of these are coming at around 111. Okay, this is close to 111. Those of you know a little bit of this will understand. So, therefore, we can obtain the majority crystal orientation from these images, which is very nice, and the inverse pole figure of this will be this image. So, you must have a little bit about how to generate these pole figures and how to study these pole figures, and then one can actually obviously obtain this kind of maps. As you say, this is 111, this is 110, this is 001, and this is actually called rolling direction, transverse direction. This is a very standard in a texture. I am not going to discuss deeply in texture in today's lecture. So, that can be done. So, using EBSD, routinely people nowadays study the texture of the material. Texture means how in a multiple grain material crystals are oriented. If there is the orientations of the crystals are haphazard, then there is no texture. If the orientation of the crystals are happening in a particular direction predominantly, then we call this a textured material. So, that can be obtained, and depending on, people can actually go on doing research on different kinds of materials, because nowadays we know that the orientation of the crystals play so much important roles in dictating the material behavior. That is why texture material is coming into picture. So, with this actually I close, and I am going to show you some example in the next lecture of texture analysis, how they can be used really to obtain information of the crystal orientations, and also to obtain the how the processing parameters can change these crystal orientations, and this can be used for the day to day applications, also very advanced applications. So, which I am going to do in the next class.